Efficient-WAM, a 1B-parameter world action model with low-cost future imagination.
Yep, that's the paper we're looking at today.
And I want you to imagine trying to pick up a coffee cup from your desk. But before your brain actually lets your hand move, it forces you to paint a photorealistic masterpiece of that cup in your mind.
Complete with, like, the reflections on the ceramic.
Exactly. The reflections of the overhead lights, the texture, everything. You would move incredibly slowly. And for years, I mean, that is exactly what we have been forcing robots to do.
Right, because world action models, or WAMs, they're incredible for giving robots physical intuition, but they are just completely bottlenecked.
Because they waste massive amounts of compute trying to generate high-fidelity, photorealistic future videos before they act. But this paper proves a fundamental shift, which is that robots do not need photorealism.
No, they really don't. They only need coarse geometry and motion cues.
Right. So the researchers here pruned a 5 billion parameter foundation model down to a 1 billion parameter mixture of transformers. They used intentionally low-resolution future latents and applied an asymmetric denoising schedule.
And the result is wild.
It's a massive 30x speedup. They cut inference latency down to just 98 milliseconds per action chunk on a standard consumer-grade RTX 4090 GPU.
Which is huge for edge deployment.
Oh, absolutely. And they do this while maintaining top-tier success rates in both RoboTwin simulations and on physical Astrobot S1 hardware. So welcome to AI Paper Slop, where we do a deep dive into the source material that's pushing the boundaries of machine learning.
And, you know, if you are an ML engineer who has ever tried deploying a visual language action model on an edge device only to watch the robot basically freeze up for 3 seconds while it thinks, this 98 millisecond latency breakthrough is exactly what you've been waiting for.
Yeah, 3 seconds is an eternity in robotics.
It really is. This paper successfully decouples generative world models from that computationally ruinous pursuit of pixel-perfect rendering. Because for a long time, I mean, the prevailing belief in the field has been that sharper, more realistic future visual predictions would naturally yield better physical actions.
Right, like better vision equals better action.
Exactly. But this research reframes efficiency. It's no longer just a hardware constraint. You know, it's a fundamental modeling problem. They're basically asking, what does the policy actually need to see to make a physical decision?
Okay, well, let's unpack the baseline bottleneck first, so we understand what we're actually improving on here. We hear a lot about these state-of-the-art world action models right now.
Sure.
But what is the actual mathematical objective they're trying to solve that makes them so incredibly slow?
Well, the standard WAM objective is to model the joint distribution of future scene evolution and control actions.
Okay, so predicting the video and the movement at the same time.
Right. In plain terms, the model takes in the current visual observation and a language command, and it tries to simultaneously predict two things: what the next few seconds of video will look like and what motor commands the robot should execute to make that future happen.
Right, and models like Modus or Pi 0.5 are highly capable at this.
They are. I mean, they're built on massive transformer backbones and process very dense visual tokens. But because they're generating high-resolution video frames alongside the actions, the computational overhead is just staggering.
Do we have a sense of exactly how slow that makes them in a real-world deployment? Because, you know, slow is subjective.
Yeah, to put it in hard numbers, predicting a single action chunk with the 8 billion parameter Modus model takes 3,215 milliseconds.
Wow.
Yeah, over 3 seconds, just to decide how to move the arm for the next fraction of a second.
Over 3 seconds, which, again, in robotics is an absolute eternity.
It's useless in a dynamic setting.
Right. If you're working in a kitchen where a pot is boiling over, or a warehouse where a human is walking by, the entire state of the world has changed by the time the robot finishes calculating its 3-second imagination of the future.
Which brings us back to your coffee cup analogy. The authors introduce a principle they call action-centric future imagination.
I like that phrasing.
Yeah, it basically means the control policy only actually needs structural cues. Think about the physics of grasping.
Okay.
The robot needs to understand the task-relevant geometry, like the shape of the handle. It needs to understand motion tendencies, like the fact that the liquid inside will slosh if you move it too fast.
Right.
And it needs to understand contact boundaries. Whether the ceramic reflects the room's lighting perfectly, or whether the background wallpaper is rendered sharply, is totally irrelevant to the motor control.
Generating those high-frequency texture details is just burning through FLOPs for no reason.
Exactly. It's a complete waste of compute.
Okay, that makes perfect intuitive sense. But how do you actually implement that? Because if the model doesn't need to render a photorealistic future, we obviously want to shrink the architecture.
Right.
But you don't want to throw the baby out with the bathwater. These massive foundation models have spent thousands of GPU hours learning how physics works.
Gravity, object permanence, friction.
Yeah, exactly. So how did the researchers intelligently shrink the model without losing that deep world knowledge?
So they built a compact mixture of transformers, or MOT framework. Instead of one monolithic network, they split the workload.
Okay.
They created a 0.8 billion parameter lightweight video expert and a 0.2 billion parameter action expert.
Got it.
The video expert's job is purely to predict the visual evolution of the scene, and the action expert's job is to extract motor commands from that prediction.
Wait, I'm stuck on something here. Getting down to a 0.8 billion parameter video expert sounds great for speed.
Yeah.
But if you just chop out like 80% of a 5 billion parameter model's brain to make it faster, shouldn't it completely forget how physics works?
Well, you don't train the smaller model from scratch.
Oh, okay.
Yeah, if you started a 0.8B model with random weights, it would lack all those deep physical priors you just mentioned. Instead, they used a technique called structured pruning on a specific foundation model.
Which one?
WAM 2.25B.
Okay, so that's a massive, highly capable video generation model.
Right. The researchers performed what's called layer slicing. They didn't just randomly delete weights. They systematically probed the 5 billion parameter backbone to identify very specific attention heads, embeddings, and feed-forward network channels.
The ones that activate when the model is processing geometry and dynamics.
Exactly. Geometry, dynamics, and physical contact.
So it's essentially a surgical extraction. They're going into the neural network and isolating the physics engine from the texture and lighting engine.
That's a perfect way to visualize it, yeah.
And then pulling only those physics pathways out to form this new 0.8B model.
Yeah, but extracting those layers is only the first step. You still have to train that sliced-down student model so it doesn't just collapse into producing total nonsense.
Right, of course.
That happens in stage 1 of their training recipe.
Huh?
And they don't just use standard flow matching.
Which is the typical process of training a model to iteratively denoise random static into a coherent image, right?
Right, because standard flow matching would just teach it to blindly recreate whatever video it saw in the training data.
Including all those useless high-frequency texture detents we just talked about trying to avoid.
Exactly. Instead, they explicitly force the 5 billion parameter teacher model to guide the 0.8 billion parameter student model. They use a teacher-guided distillation loss.
How does that actually work computationally?
Well, they run the same input through both the massive teacher and the tiny student. The loss function calculates the mean squared error, the mathematical difference between the intermediate hidden states of the student and the teacher.
So they're literally comparing the hidden states.
Yeah. And crucially, it specifically aligns the temporal frame-to-frame changes.
Meaning the motion cues.
Correct. The student is explicitly mathematically penalized if it fails to capture the dynamic evolution of the scene exactly the way the 5B model predicted it would move.
Wow.
Yeah, it forces the 0.8B model to prioritize structural and dynamic accuracy over visual fidelity. It becomes highly action-centric.
Okay, so we've successfully shrunk the brain of the model. We are down to 1 billion parameters total between the two experts.
Yep.
But if that brain is still looking at high-definition, dense video frames, the processing time is still going to be massive.
Right, because of the tokens.
Because the computational cost of attention mechanisms scales quadratically with token density. You double the amount of pixels you're looking at. You basically quadruple the amount of math a transformer has to do.
Exactly.
So how did they solve the visual data problem?
This leads to their second major optimization, the multi-scale video latent layout. Usually, world action models predict future videos at the exact same uniform resolution as the input observation. If the robot looks at the world in high definition, it imagines the future in high def. Efficient-WAM breaks this symmetry.
Just to ground this for everyone, when they process these visual frames, they are running them through a VAE, a variational autoencoder.
Right, standard procedure.
So we're talking about compressing that raw visual pixel data down into its most essential mathematical representation, which we call latents or tokens.
Yeah, you're taking a high-dimensional image and mapping it to a lower-dimensional latent space that the transformer can actually process efficiently.
Okay, so what does Efficient-WAM do differently with the VAE?
So the current observation, what the robot is looking at right now, is encoded through the VAE into high-resolution condition tokens, specifically a spatial resolution of 384 by 320.
That's pretty standard.
But the target future frames, the imagination of what will happen next, are spatially downsampled to a much lower resolution, down to 192 by 160, before they are ever encoded by the VAE.
Wait, so they are intentionally degrading the resolution of the future?
Yes.
How much compute does that actually save?
A tremendous amount. That spatial downsampling drops the future token count from 240 tokens per frame down to just 60 tokens per frame.
Oh, wow.
Yeah, you're slashing the density of the future imagination by 75%.
But hold on, I have to push back here. If the robot's imagination of the future looks like a blurry, pixelated mess, doesn't that inherently lead to inaccurate, sloppy physical actions?
That's what you would think, right?
Yeah. I mean, if I'm trying to thread a needle or grip a really fragile object, and my mental model of the future is fundamentally blurry, how does the robot know exactly where to put its grippers?
It's a highly intuitive concern, but it kind of misunderstands how the joint attention mechanism operates under the hood.
Okay, explain it to me.
The genius here lies in concatenating or linking together these multi-scale latents. Remember, the current frame remains at high resolution.
Right.
So the action expert still has absolute high-fidelity spatial details of the present state. It knows exactly where the sharp object boundaries are right now in physical space.
Ah, I see. So it isn't flying blind.
Not at all. The token-sparse low-resolution future latents are simply appended to that high-resolution present sequence.
So the blurry future merely serves as a course dynamic guide for where things are going to move.
Exactly. The model cross-references the high-resolution present with the low-resolution future trajectory to extract the precise control signals.
That is so smart.
Yeah, you do not need sharp future edges if you already have sharp present edges and a clear understanding of the mathematical motion vector.
Okay, so it uses the blurry future as a directional hint, basically a motion path, while relying entirely on the sharp present for the actual precise motor coordination.
Exactly.
That is incredibly clever. Okay, so the model weights are smaller, and the token count is slashed by 75%. But there's still one massive computational sink left, which is the iterative sampling process itself.
You're referring to the flow matching generation loop.
Exactly. Because in diffusion or flow matching models, generation isn't a one-and-done calculation. You start with noise, and you have to loop through multiple denoising steps.
Right, refining the prediction over and over again until it forms a coherent output.
And every single step requires a full pass through the neural network. So if you need 10 steps to generate an action, you're running that model 10 times.
In traditional generative WAMs, force both the video prediction branch and the action generation branch to share that exact same iterative denoising schedule.
So they're locked together.
Yep. If the policy determines that it needs 10 steps of refinement to guarantee a precise, safe robotic action, the architecture forces the model to also compute 10 steps of video generation.
Which, as we've established, is largely a waste of compute, since we don't really care about the fine visual details that emerge in those later steps.
Exactly. So Efficient-WAM bypasses this entirely with an innovation they call training-free asymmetric video action denoising.
Okay, what does that asymmetry actually look like in practice? How do they split it?
They landed on a really aggressive configuration, a 2-10 split.
Wait, just 2?
Yeah. That means the model only performs 2 denoising steps for the video branch, while the action branch gets the full 10 steps of refinement.
That's crazy. It's like an artist doing a quick, rough 2-second pencil sketch of a scene just to know where the objects are, and then spending 10 minutes carefully drawing the exact hand movements over that sketch.
That's a great analogy, instead of trying to oil paint the entire scene from scratch.
But why does just 2 steps work? I mean, how can the action branch derive anything useful from a video prediction that was halted after only 2 iterations of denoising? It must still look mostly like static.
The mechanics behind why this works are deeply rooted in how structure resolves during flow matching.
Okay.
When a model transforms noise into data, it doesn't resolve all features simultaneously. Low-frequency data emerges first.
Global structural cues.
Right. The basic object geometry, the rough positioning, the major contact boundaries, those emerge from the noise very early, typically within the first 1 or 2 steps.
So the physics basically reveals itself first.
Exactly. The remaining steps in a standard generation process, steps 3 through 10, are almost entirely spent hallucinating the high-frequency details.
The lighting, the micro textures, the reflections.
Yep. By halting the video generation after just 2 steps, the researchers save massive amounts of compute.
So the model just caches those early-stage, structurally sound video features.
and reuses them to condition the remaining 8 steps of the action refinement.
That is brilliant. The action branch gets the full sampling depth it needs to calculate a safe physical trajectory, while the video branch is literally put to sleep the moment the structural dynamics become actionable.
It's all about pruning away unnecessary work.
Okay, we've walked through all the major theoretical optimizations. We have the surgical MOT layer slicing, the multi-scale latents lowering the token count, and the asymmetric denoising saving us from looping through useless video generation.
Yeah.
It sounds incredibly elegant on paper, but, in robotics, elegance doesn't matter if the robot drops the ball. Let's look at the empirical results. They started in simulation, right?
Yes, they evaluated the model in the RoboTwin 2.0 simulation environment. They ran it across 50 distinct manipulation tasks.
Okay, and how did it do?
The 1 billion parameter Efficient-WAM achieves an 86.7% clean success rate.
That sounds pretty high.
It is. To put that in context against the landscape of current research, it easily outperforms larger VLA models like the 4 billion parameter Lingbot and even the 5 billion parameter GigaWorld policy.
Wow. And how did it compare against the massive 8 billion parameter Modus model we talked about earlier, the one that takes 3 seconds to think?
It trails Modus by only 2%.
Are you serious?
Yeah. So they've shed 87% of the total parameter count, heavily degraded the future visual resolution, truncated the video denoising process, and the cost was a mere 2% drop in simulated task success.
But simulation is one thing. The physics are perfect, the lighting is controlled, there's no sensor noise. Real-world physics is messy. Oh, absolutely.
I see they deployed the fully optimized version, which they call Efficient-WAM art, onto actual physical hardware. They use the Astrobot S1.
And the real-world deployment is where this paper truly shines, because it proves why latency is the ultimate bottleneck in robotics.
Okay, what kind of tasks did they test?
They ran 20 trials per task across a variety of challenges, things like pipette tray grasping, reagent bottle transfer, sorting Legos by color, and fine-grained pen uncapping.
Okay, and the results. Did that 2% simulation gap hold up?
Actually, the results flipped. Efficient-WAM achieved a 66.25% average success rate across those complex physical tasks.
Wait, that beats Modus.
Yeah, it actually beats the massive 8 billion parameter Modus baseline, which sat at 63.75%.
But wait, how is that possible? The smaller, heavily pruned, lower resolution model beat the massive foundation model in the real world. It has a worse imagination of the world by design.
It beats the larger model precisely because of the latency reduction.
Right. Remember, Modus is sitting there calculating for 3,215 milliseconds before it outputs an action chunk. Efficient-WAM drops that latency down to just 98 milliseconds on a local RTX 4090.
That is a 32x speedup.
Yeah, it's the difference between open loop and closed loop control.
Okay, explain that difference for us.
Heavyweight generative models force a robot into sluggish, start and stop, open loop execution. The robot looks at the scene, freezes for 3 seconds to calculate its perfect photorealistic future, executes a rigid movement, and then has to freeze again.
And in the real world, the environment changes during those 3 seconds. Objects slip, lighting shifts, momentum carries things further than expected.
Exactly. But by breaking the 100 millisecond barrier, Efficient-WAM unlocks fluid, closed-loop manipulation. The robot is reacting 10 times a second.
Oh, I see. It doesn't need a perfect plan because it can continuously replan and adjust its microactions on the fly based on real-time visual feedback.
Right. That adaptability is why its success rate surpasses the heavier, slower model. It's reacting instead of just predicting.
It shifts the paradigm from perfect planning to rapid correction. And in real-world physics, rapid correction almost always wins.
Definitely.
But there is no such thing as a free lunch in machine learning architecture. Every optimization is a trade-off. Where does trading visual resolution for speed fail? Like, where are the absolute limitations of this approach?
Well, the researchers are very transparent about the edge cases where this methodology breaks down.
Okay, what are they?
The low-resolution future latents and the truncated video denoising are highly effective for macroscopic manipulation. Grabbing bottles, sorting blocks, moving objects across a table.
Big movements.
But for extreme micromanipulation tasks, things like inserting a tiny thread into a needle or ultra-precise industrial assembly, this approach struggles.
Because in those specific cases, the pixel-level precision of the future state is actually required to verify physical tolerances.
Yes. When you are dealing with sub-millimeter tolerances, the blurriness of the future prediction can lead to fine spatial misalignment,
So the robot's end effector might be off by just 2 or 3 millimeters.
which is irrelevant when grabbing a coffee cup, but results in a hard contact collision or a misgrasp when inserting a microchip.
So what does this all mean for the listener who might be building or researching these systems right now? One glaring limitation that jumps out to me is the reliance on static inference schedules.
Right.
Right now, that asymmetric denoising split is hard-coded, isn't it? It is always exactly 2 steps for video and always 10 steps for action, regardless of what the robot is actually trying to do.
That is currently hard-coded, yeah, and it points to a massive opportunity for future research, dynamic compute allocation.
Oh, that sounds interesting.
Imagine a control policy that doesn't use a fixed rigid schedule. Instead, it dynamically scales its video denoising budget based on the scene entropy or the perceived task difficulty.
So if it's doing a simple transfer task, just moving a block from point A to point B, it uses one video step and zips through it.
Exactly. But if it detects high uncertainty, severe visual occlusions, or a complex micro-manipulation task requiring high-precision physical interactions, the policy could dynamically allocate 5 or even 8 steps to the video branch.
So it would intentionally slow itself down to sharpen its internal imagination only when the physics of the task strictly demand it.
Right, developing that kind of adaptive compute routing would push this efficiency paradigm even further.
Bridging the gap between rapid macroscopic reflexes and precise microscopic planning.
Exactly.
That is a fascinating frontier for the field to explore next. We've covered the MOT slicing, the multi-scale latents, the asymmetric denoising, and how they all combine to shatter the 100 millisecond latency barrier for world action models. Thank you for joining this deep dive into the source material on AI Paperslop.
Yeah, thanks for listening.
And to leave you with a final thought to ponder, if an artificial intelligence can achieve real-time, closed-loop physical control by intentionally blurring and degrading its internal imagination of the future just to save compute, what does that say about how biological brains process the world?
That's a deep question.
Are human reflexes and our own split-second physical decisions just a biological form of asymmetric denoising? Do our brains instinctively ignore the high-fidelity details of our environment to ensure we can react and act in time? It's something to think about. We'll catch you on the next deep dive.